Our universe began not with a whisper, but with a roar. For decades, the Big Bang Theory has stood as our best story of cosmic origin, describing a fiery birth from an unimaginably dense state. But the full story is far stranger and more magnificent. We have uncovered 25 incredible discoveries that reshape this narrative, including a breathtaking moment of hyper-expansion called cosmic inflation that solved the universe's deepest puzzles. By the end, you will understand not just how our cosmos began, but how the tiniest quantum whispers grew into galaxies. Why does the afterglow of creation look the same in every direction, a fact that once threatened to break the entire theory? What mysterious force is now ripping space itself apart? The journey from nothing to everything is written in the light of the first dawn. What part of this cosmic story surprises you the most? That roar of creation left a permanent echo. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a strange, persistent hiss in their giant horn antenna in New Jersey. They pointed it at the sky and the hiss remained. They pointed it at New York City and the hiss remained. They even famously cleaned out a pair of nesting pigeons and their, well, droppings, thinking it was radio interference. Yet the faint, uniform static persisted in every direction they looked. They had not found a technical flaw. They had stumbled upon the oldest light in the universe, the cosmic microwave background. This was the afterglow of the Big Bang itself, cooled and stretched by 14 billion years of cosmic expansion. It is the relic radiation from a pivotal moment when the universe was just 380,000 years old. Before that moment, the cosmos was a searing, opaque fog of plasma, too hot for light to travel freely. As it expanded and cooled, electrons and protons finally combined to form neutral atoms, and the universe suddenly became transparent. That first flash of light, once blindingly hot, has been traveling ever since, its waves stretched by the expanding fabric of space into the microwave part of the spectrum. Today, it fills the entire sky with a nearly perfect, frigid glow of just 2.7 degrees above absolute zero. Its discovery was the smoking gun, the definitive proof that our universe did indeed emerge from an incredibly hot, dense state. But this profound evidence presented cosmologists with a new and baffling puzzle. How could regions of the universe on opposite sides of the sky, regions that could never have communicated with each other even at the speed of light, have reached exactly the same temperature? This perfect uniformity whispered of a deeper, stranger beginning. That faint cosmic hiss was not the first clue to a dynamic universe. Decades before Penzias and Wilson heard the echo, another astronomer was making a discovery that would forever change our cosmic perspective. In the late 1920s, Edwin Hubble was using the powerful new 100-inch Hooker telescope at Mount Wilson Observatory. He was meticulously studying the faint, fuzzy nebulae that dotted the sky, measuring their distances. At the same time, other astronomers like Vesto Slipher had been analyzing the light from these nebulae, finding their spectral lines were mysteriously shifted toward the red end of the spectrum. Hubble combined these two sets of data, distance and redshift, and made a staggering announcement in 1929. The farther away a galaxy is, the faster it appears to be moving away from us. Its light is stretched, reddened by this motion. This was not just a few galaxies rushing off in random directions. It was a clear, linear pattern across the cosmos, a pattern we now call Hubble's law. The entire fabric of space itself was stretching, carrying the galaxies along with it like raisins in an expanding loaf of bread. Think of the redshift as a cosmic speedometer written in light. If a galaxy's light is shifted slightly red, it is moving away modestly. If the light is dramatically stretched, shifted far into the red, that galaxy is receding at a tremendous fraction of the speed of light. This single observation was the key that unlocked the modern view of the cosmos. It proved the universe was not static and eternal, as even Einstein had once believed. It was dynamic, evolving and growing. Now follow that logic backward. If space is expanding today and galaxies are moving apart, then yesterday they were closer together. A year ago, closer still. Run the cosmic film reel backward in your mind through millions, then billions of years. All the matter and energy we see, every star in every galaxy, was once compressed into an unfathomably hot, dense and tiny point. That inevitable conclusion, drawn directly from Hubble's graph of redshift and distance, is the very heart of the Big Bang theory. The universe had a beginning. But if everything was once in that singular state, how did it get so perfectly smooth? The cosmic microwave background showed us the stunning uniformity, but the expansion Hubble discovered seemed to make that uniformity impossible. Hubble's expanding universe gave us the when and the how, but it could not tell us what the early cosmos was actually made of. For that, we must peer into the first few minutes, into a furnace of unimaginable intensity. Picture the entire observable universe, all its future galaxies and stars, compressed into a space smaller than our solar system. In that primordial inferno, the temperature was over 1 billion degrees, and the density was like the core of a star, but everywhere. This was not just a hot soup of particles, it was the universe's only moment as a perfect nuclear fusion reactor. We call this brief, spectacular epoch Big Bang nucleosynthesis. For roughly the first 3 minutes after the beginning, conditions were just right for nuclear alchemy. Protons and neutrons, which had formed from even more fundamental particles in the first second, slammed into each other with tremendous energy. They fused to form the nuclei of the lightest elements. Deuterium, a heavy form of hydrogen, formed first, then helium nuclei, each containing 2 protons and 2 neutrons, began to assemble. Trace amounts of lithium, the third lightest element, were also forged, but this cosmic forge had a very short timer. As the universe continued its relentless expansion, it cooled with breathtaking speed. Within minutes, the temperature dropped below the threshold needed to sustain nuclear fusion. The reactor shut down, freezing the elemental abundances in place. And here lies one of the most precise and beautiful predictions of the Big Bang theory. Physicists like George Gamow, Ralph Alpher, and Robert Herman calculated the exact ratios of these light elements that should have been produced during those first 3 minutes. Their math said the universe should be, by mass, about 75% hydrogen, 25% helium, and just a tiny, trace amount of lithium. For decades, this was just a theoretical prediction. Then astronomers developed the tools to test it. They pointed their telescopes not at stars, which cook and recycle elements in their cores, but at the most pristine, ancient gas clouds in the distant universe. These are cosmic relics, clouds of gas that have never been polluted by later generations of stars. When they analyze the light from these primordial clouds, the data reveals a stunning truth. The observed abundances of hydrogen, helium, and lithium match the Big Bang predictions with remarkable precision. It is a perfect cosmic fingerprint. No other process we know of could have produced this specific pattern of the lightest elements across the entire cosmos. This is not a rough estimate. It is a precise receipt from the universe's first transaction, stamped 3 minutes after time began. It tells us that our story of an expanding, cooling fireball is not just a compelling idea, it is a fact written into the very fabric of matter itself. Yet, even with this triumph, the mysteries were only deepening. If the early universe was this hot, dense, and uniform, how did anything ever clump together to form the stars and galaxies we see today? That perfect receipt from the first 3 minutes came with a profound contradiction. The cosmic microwave background, that ancient afterglow, displays a temperature that is uniform to an almost unbelievable degree. No matter which direction we look, the temperature of that primordial light is the same, varying by less than 1 part in 100,000. This exquisite smoothness is the foundation of our orderly universe. Yet, according to the classic Big Bang model, it is also completely impossible. This is the horizon problem, one of the most elegant and devastating puzzles in cosmology. To understand why, think about communication. In our everyday world, if you want two rooms to reach the same temperature, you open a door or turn on a ventilation system. Heat travels from one area to another until equilibrium is reached. In the universe, the ultimate speed limit for any such communication or smoothing is the speed of light. Information, influence, even heat cannot travel faster. Now, look at the cosmic microwave background coming from 2 points on opposite sides of the sky. When that light was emitted, the universe was only 380,000 years old. In all that time since the Big Bang, light could only have traveled a finite distance. We can calculate a cosmic horizon, the maximum distance any signal could have possibly crossed. The shocking result: those 2 opposite points on the sky were separated by a distance roughly 90 times greater than the maximum distance light could have traveled. They were, by the strict rules of physics, causally disconnected. They were like 2 people stranded on islands so far apart that no message, no boat, no signal fire could ever reach from one to the other. And yet, somehow, these 2 isolated islands decided to have exactly the same climate, down to a minuscule fraction of a degree. How could regions that had never been in contact, that had never exchanged a single photon of energy, possibly know to coordinate their temperatures so perfectly? The classic Big Bang model had no answer. It suggested the universe was born with this perfect smoothness as a sheer, inexplicable coincidence, a finely tuned initial condition. For many scientists, that was deeply unsatisfying. It hinted that our story was incomplete, that something must have happened in the universe's first fleeting moments to connect these disconnected horizons, to iron out any wrinkles and set the stage for that perfect uniformity. The cosmos needed a mechanism to smooth itself out faster than light itself could travel, a concept that seems to defy everything we know. But what if, in those first instants, the rules were profoundly different? The horizon problem was not the only impossible coincidence. A second, equally profound mystery lurked in the geometry of space itself, a puzzle known as the flatness problem. Our universe, on the largest scales we can measure, appears to be geometrically flat. This is not flat like a sheet of paper, but flat in the cosmic sense of parallel lines staying parallel forever, and the angles of a triangle adding up to exactly 180 degrees. This observed flatness is a direct consequence of the universe's density. Think of the cosmos as having a critical density, a perfect balance point between expansion and collapse. If the actual density were higher than this critical value, the gravitational pull of all the matter and energy would eventually overcome the expansion, causing the universe to curve in on itself and ultimately crunch back down in a big crunch. That geometry is called closed, like the surface of a sphere. If the density were lower, gravity would be too weak to ever rein in the expansion, leading to a universe that curves outward like a saddle, growing forever cold and empty. That is an open geometry. Our observations, from the cosmic microwave background to the motions of galaxies, tell us we live in a universe that is balanced right on that knife edge of flatness. The problem is how unbelievably precarious that balance is. For the universe to look as flat as it does today, 14 billion years after the Big Bang, its density in the first second had to be fine-tuned to an astonishing precision of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. To put that in perspective, it is like balancing a pencil on its tip for billions of years, or hitting a bullseye on a target the size of the entire observable universe. The classic Big Bang model offered no reason for this. It simply said the universe was born with this exquisitely precise density, an initial condition of unimaginable perfection. To many physicists, this level of fine-tuning felt deeply unnatural, like finding a watch perfectly set to the right time in the middle of a wilderness. It screamed for a physical process, a mechanism that could dynamically drive the universe toward flatness, no matter what its starting conditions were. The cosmos needed a way to erase any initial curvature, to stretch space so violently that any bend or warp would be smoothed out into apparent flatness, just as inflating a balloon makes its surface look flatter and flatter from the perspective of a tiny ant crawling on it. Without such a process, our existence in this stable, flat universe would be a statistical miracle, and miracles in science are usually clues that we are missing a fundamental piece of the story. These two impossible coincidences, the horizon and flatness problems, were a glaring signal that our cosmic origin story was missing its first chapter. Then, in one brilliant flash of insight, a young physicist named Alan Guth provided the missing prologue. In 1980, Guth was wrestling with problems in particle physics when he realized the early universe could have undergone a phase of supercooling. This led him to a revolutionary idea he called cosmic inflation. Imagine the universe in its first incomprehensibly tiny fraction of a second, perhaps at 10 to the minus 36 seconds old. At that moment, a strange and powerful energy field, which physicists now call the inflaton field, came to dominate the cosmos. Think of this field as a kind of latent energy trapped in the very fabric of space itself, like a universe-wide version of water supercooled below its freezing point but not yet crystallizing. This unstable state possessed a remarkable property. It caused the fabric of space to expand, not at the steady rate we see today, but at an exponential, explosive pace. The numbers are almost beyond comprehension. In a span of time so brief it makes a blink seem eternal, the universe doubled in size and then doubled again and again, over 100 times in succession. This period of inflation stretched a region of space smaller than a subatomic particle to a size larger than our entire observable universe in less than a trillionth of a second. This single, breathtaking idea solved both of our profound puzzles at once. The horizon problem vanished because the entire sky we see today was once a single, tiny, causally connected patch. Before inflation, every part of that patch had plenty of time to exchange energy and reach a uniform temperature. Then, inflation acted like a cosmic magnifying glass of unimaginable power, stretching that tiny, smooth patch across the entire sky. What we see as opposite horizons were once neighbors, intimately linked before being blown apart. The flatness problem dissolved just as elegantly. No matter what shape or curvature the infant universe had, this hyper-expansion would have stretched it until it appeared perfectly flat, just as blowing up a balloon makes any small wrinkle on its surface disappear from view. Inflation dynamically drove the universe toward that critical density, making flatness not a miraculous starting condition, but a natural outcome of a brief, violent event. With this single theoretical leap, the bizarre fine-tuning of the classic Big Bang was replaced by a compelling physical mechanism. Inflation did not just solve old problems, it made a series of startling new predictions about what we should see in the cosmos today. It promised that the seeds for all cosmic structure were born in that explosive moment, not as flaws but as quantum whispers. The quantum realm holds the secret to our very existence. Inflation's most profound prediction is not just about smoothness, but about the necessary imperfections that gave rise to everything. In that same incomprehensibly brief moment of hyper-expansion, the universe was not perfectly uniform on the smallest scales. According to quantum mechanics, empty space is never truly empty. It is a seething, bubbling foam where particles and energy flicker in and out of existence in fleeting quantum fluctuations. These are microscopic ripples in the fabric of reality itself. In the infant universe, the inflaton field was also subject to these same quantum jitters. As inflation began, these infinitesimal fluctuations in the field were caught in the act and stretched to unimaginable proportions. Picture a tiny, random wrinkle on the surface of a deflated balloon. Now imagine inflating that balloon to the size of the Earth in an instant. That tiny wrinkle becomes a vast rolling hill. That is precisely what inflation did to those quantum whispers. The microscopic became macroscopic. These stretched ripples translated into minute differences in the density of matter and energy across the newly expanded cosmos. Where the inflattened field was slightly denser, space expanded just a tiny bit more slowly. Where it was slightly less dense, expansion was a fraction faster. The result was a subtle pattern of over-dense and under-dense regions imprinted across the entire universe, a cosmic fingerprint of quantum uncertainty. These over-dense patches, these gravitational seeds, were crucial. After inflation ended and the normal Big Bang fireball took over, gravity got to work. It is an attractive force pulling matter toward areas of higher density. Over hundreds of millions of years, gravity amplified those tiny differences. The slightly denser regions pulled in more and more gas from their surroundings, growing steadily. They became the nurseries for the first stars, the cores of the earliest galaxies, and the great clusters and superclusters we map today. Every galaxy, every star, every planet, and every atom in your body can trace its ultimate origin back to those quantum fluctuations magnified by inflation. Without them, the post-inflation universe would have been a perfectly smooth, utterly boring sea of particles. There would be no clumps, no structures, no stars to forge heavy elements, and no planets to orbit them. We owe our complex, structured cosmos to the fundamental randomness of the quantum world, stretched across the heavens in a flash. But if this prediction is true, where can we possibly look for evidence of these primordial seeds? The quantum seeds planted by inflation were not scattered randomly. They carried a specific, elegant signature, a cosmic blueprint that would dictate how galaxies would later cluster across the vastness of space. This pattern is known as a nearly scale invariant spectrum. It is one of inflation's most precise and beautiful predictions. Scale invariance is a subtle but powerful concept. Imagine you are looking at a map of the universe and you zoom in on a region 100 million light-years across. You measure how much the density of matter varies from point to point within that region. Now zoom out to a region 1 billion light-years across and take the same measurement. In a perfectly scale-invariant universe, you would find roughly the same magnitude of fluctuation, the same amount of lumpiness on both of those vastly different scales. The quantum jitters that inflation stretched were like a fundamental note played across every possible wavelength of the cosmos. Whether you examine the universe on the scale of a future galaxy cluster or an entire supercluster, the initial strength of those gravitational seeds should be nearly identical. Why is this so significant? Because it tells us something profound about the nature of the inflationary energy itself. The fact that the fluctuations came out almost but not perfectly, scale invariant, suggests the inflattened field was changing very, very slowly as it drove the expansion. It was like rolling down an incredibly gentle, almost flat hill. A steeper, more dramatic roll would have produced a very different pattern of fluctuations, one where large scales looked dramatically different from small scales. The near-scale invariance became a key testable signature, a specific prediction etched into the fabric of the cosmos that astronomers could go out and hunt for. But where could they possibly find a map of the universe's density from a time before any stars or galaxies existed? They needed to look at the oldest photograph we have, the cosmic microwave background. The subtle temperature differences in that afterglow are direct traces of those primordial density fluctuations. Where matter was slightly denser, gravity was a bit stronger, which created a slight gravitational well. Photons climbing out of that well lost a tiny bit of energy, making that spot in the sky appear ever so slightly cooler. Conversely, under dense regions appear as faint warm spots. By meticulously mapping these tiny temperature variations across the entire sky, scientists could reconstruct the spectrum of those initial seeds. They could measure whether the fluctuations on large angular scales matched the strength of those on small scales. Finding that nearly scale-invariant pattern would be a smoking gun for inflation, a direct link between the quantum foam of the first instant and the large-scale structure of our universe. It turned a philosophical idea into a hard, numerical prediction waiting to be confirmed or refuted by the data. The hunt for those quantum seeds became one of the greatest detective stories in modern science. For decades after its discovery, the cosmic microwave background appeared frustratingly smooth. Satellites and high-altitude balloons measured it, but their instruments could only see the broad, uniform glow, not the subtle fingerprints of the primordial lumps. The theoretical prediction was clear. Inflation demanded those tiny temperature variations, but the technology to see them did not yet exist. Then, in 1989, NASA launched the Cosmic Background Explorer, or COBE satellite. Its mission was audacious: to measure the temperature of the cosmic afterglow with a precision of 1 part in 100,000, to see if the universe's baby picture had any texture at all. For years, the COBE team, led by George Smoot and John Mather, painstakingly collected data, filtering out the glare of our own galaxy, the microwave hum from Earth, and every other source of interference. The universe held its breath. Finally, on April 23, 1992, at an American Physical Society meeting, the team unveiled their result. They presented a map of the entire sky, a splotchy, mottled oval of blues and reds. It was not a uniform sheet. It was a tapestry of minute temperature differences, variations of just 30 millionths of a degree. These were the anisotropies, the wrinkles in time. George Smoot famously said it was like seeing the face of God. What the world saw was the first direct image of the infant universe's lumpiness, the very gravitational seeds that inflation had predicted. Each of those tiny cold and warm spots corresponded directly to an over-dense or under-dense region in the primordial plasma. The slightly cooler blue patches were places where matter was a bit more concentrated, the gravitational wells from which the first galaxies would eventually coalesce. The warmer red patches were the future cosmic voids. COBE WMAP was not just a confirmation, it was a revelation. It proved the universe was not born perfectly smooth. It was imprinted at birth with a specific pattern of imperfections, a pattern whose statistical properties matched the predictions of a near-scale invariant spectrum with stunning accuracy. The quantum whispers from the first instant had been found, fossilized in the light of the cosmic dawn. This was the moment cosmology transitioned from a speculative history into a precision science. We had our blueprint, but a new question immediately arose. COBE saw the large-scale lumps, the continents of the early cosmos. To truly understand the blueprint, scientists needed to see the fine print, the hills and valleys that would become individual galaxy clusters. They needed a map with far greater resolution. COBE had given us the continents, but the fine details of the cosmic blueprint were still a blur. The next great leap in our understanding required a map of breathtaking precision, a task taken up by a remarkable spacecraft named the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, WMAP was not just an upgrade, it was a revolution in cosmic cartography. For 9 years, it observed the cosmic microwave background from a stable gravitational point 1 million miles from Earth, free from our planet's thermal interference. Its mission was to measure those tiny temperature variations with a sensitivity and angular resolution far beyond anything before. When it beamed its data back, it did not just give us a better picture, it gave us the universe's birth certificate, written in numbers of astonishing clarity. WMAP measured the exact statistical properties of the hot and cold spots in the afterglow, the size of the lumps and the spacing between them. From this intricate pattern, scientists could extract fundamental cosmic parameters as if reading a detailed medical chart. It determined the universe's age with unprecedented certainty, 13.8 billion years, plus or minus a mere 37 million. That is like knowing the age of a 40-year-old person within 2 months. It precisely quantified the composition of the cosmos, revealing a shocking recipe. Only about 4.6% of the universe is the ordinary atomic matter that makes up stars, planets, and us. About 24% is the mysterious, invisible gravitational glue known as dark matter, and a dominant 71% is the even more enigmatic dark energy, the force accelerating the expansion of space itself. Most definitively, WMAP confirmed the universe's geometry is flat within a margin of error of just 0.5%, a stunning validation of inflation's core prediction. Every piece of data from WMAP exquisite map fit together like a perfect puzzle, each parameter reinforcing the others within the framework of an inflationary Big Bang. It was no longer just a compelling theory, it was a precise, quantitative model of our cosmic origin. We had moved from seeing the face of the infant universe to taking its temperature, weighing it, and measuring its shape. Yet, with such profound answers, even deeper questions emerged. If the universe is flat and dominated by dark energy, what does that tell us about its ultimate fate? And what could possibly have generated the specific pattern of seeds that WMAP saw so clearly? WMAP was a masterpiece, but the Planck satellite would paint the ultimate portrait of creation's dawn. Launched by the European Space Agency in 2009, Planck was a technological marvel, designed to observe the cosmic microwave background with a sensitivity and resolution that pushed the very limits of physics. For over 4 years, it scanned the entire sky from a vantage point 1 million miles away. Its instruments cooled to just a fraction of a degree above absolute zero to detect the faintest whispers of the ancient light. When it released its final data in 2013, it did not overturn our story. Instead, it etched it in stone with breathtaking precision. Planck's map is the sharpest, most detailed image of the infant universe we will likely ever have, a snapshot of the cosmos at 380,000 years old with a clarity that feels almost voyeuristic. Every subtle swirl and faint blotch in that microwave tapestry is a data point of immense power. Planck measured the temperature fluctuations down to variations of a few millionths of a degree, and it did something more. It meticulously mapped the polarization of that light, a subtle directional property that carries its own story. With this unparalleled data, cosmologists could perform the most rigorous test of cosmic inflation ever conceived. The results were a resounding yet nuanced confirmation. The pattern of hot and cold spots, their sizes and distribution, matched the predictions of the simplest inflationary models with astonishing accuracy. The universe's geometry was measured to be flat with a certainty of 99.99%, eliminating virtually any doubt. Planck also tightened the cosmic recipe, refining the amounts of ordinary matter, and dark energy to a single decimal place. But perhaps its most profound gift was revealing subtle imperfections in the blueprint itself. Remember the prediction of a nearly scale-invariant spectrum. Planck found that nearly was the operative word. The data revealed a slight but definitive tilt, a gentle preference for larger-scale fluctuations over smaller ones. This tiny deviation from perfection is not a flaw, it is a crucial clue. It tells us that the inflattened field was not rolling down an impossibly flat hill, but one with a gentle, graceful slope. The specific angle of that tilt, measured by Planck, helps rule out entire families of inflationary models and points toward the specific kind of physics that might have driven the hyper-expansion. It is as if we had a fossil and Planck allowed us to count its microscopic growth rings, revealing not just its age but the climate in which it was born. The mission delivered the ultimate validation of inflation's core ideas while simultaneously opening a window into the mysterious energy that powered it. We moved from confirming the story to reading the fine print of the first chapter, written in the language of quantum gravity. The Planck satellite's exquisite map told us what happened, but a deeper signature could reveal how it happened. Within the faint polarization of the cosmic microwave background, scientists predicted a specific swirly pattern known as B-mode polarization. This would be the ultimate smoking gun for cosmic inflation. To understand why, we must go back to that first explosive instant. The violent stretching of space during inflation would have shaken the very fabric of spacetime itself, generating ripples known as primordial gravitational waves. These are not waves in space, but waves of space, distortions in the geometry of the universe that propagate at the speed of light. As these waves passed through the primordial plasma just before the cosmic microwave background was released, they would have imparted a distinct twisting, curling pattern onto the polarization of that ancient light. Finding these B-modes would be direct evidence of inflation's most dramatic moment, a fingerprint of quantum gravity imprinted on the sky. The hunt for this signal became one of cosmology's holy grails. Teams built incredibly sensitive telescopes at the driest, coldest places on Earth, like the South Pole, where the thin, stable atmosphere allows for pristine observations of the cosmic microwave background. In March 2014, one of these collaborations, called BICEP-2, made a stunning announcement. They believed they had detected the long-sought B-mode polarization at a level that pointed to a spectacularly energetic version of inflation. The scientific world erupted with excitement. Headlines proclaimed the discovery of gravitational waves from the Big Bang, a confirmation of inflation that seemed almost too good to be true. And it was. The BICEP-2 team had observed from the South Pole, but they had not fully accounted for a confounding foreground, the faint, swirling emission from cosmic dust within our own Milky Way galaxy. This galactic dust can also polarize light and create patterns that mimic the primordial B-mode signal. When the Planck satellite released its full sky map of galactic dust later that year, a sobering cross-analysis revealed that most, if not all, of the BICEP-2 signal could be explained by this local interference. It was a powerful lesson in cosmic humility. The search for primordial B-modes is like trying to hear a whisper at the edge of a hurricane. You must first understand and subtract the roar of the storm, which in this case is the complex emission from our galaxy. The episode did not disprove inflation, but it highlighted the extraordinary difficulty of the quest. It set a new, more rigorous standard for the search, requiring ever more precise measurements of both the cosmic microwave background and the galactic foreground. The dream of seeing inflation's gravitational wave signature remains alive, driving the next generation of experiments to even more remote locations and even into space. If they succeed, it will be a direct look at the universe's first tremor. The search for primordial gravitational waves continues, but another cosmic mystery was already reshaping our understanding of the universe's fate. In the late 1990s, two independent teams of astronomers were using distant stellar explosions to measure how quickly cosmic expansion was slowing down. They were studying a specific type of supernova called a Type 1a, which acts as a standard candle. Because these explosions always reach roughly the same intrinsic brightness, astronomers can determine their true distance by measuring how dim they appear from Earth. They then compare that distance to the supernova's redshift, which tells how much the universe has stretched since the blast occurred. By looking at extremely distant and therefore ancient supernova, the teams could chart how the expansion rate has changed over billions of years. Everyone expected to see the deceleration caused by gravity's relentless pull on all the matter in the cosmos. The only question was by how much. The data, however, told a completely different story. The most distant supernovae were fainter than they should have been. This meant they were farther away than anyone had predicted. The stunning conclusion, announced in 1998, was that the expansion of the universe is not slowing down at all. It is accelerating. Something is pushing galaxies apart with ever-increasing force. This discovery was so revolutionary and unexpected that it earned the lead researchers the Nobel Prize in Physics in 2011. The mysterious something causing this acceleration was given a name: dark energy. It is not a substance we can touch or see, but rather a property of space itself, a kind of latent repulsive energy woven into the fabric of the cosmos. Its effect is the opposite of gravity. It pushes things apart on the largest scales. Measurements from supernova, the cosmic microwave background, and galaxy surveys have since converged on a shocking cosmic budget. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible gravitational scaffold, accounts for about 27%. And all the ordinary matter that makes up stars, planets, and us constitutes a mere 5%. We are living in a universe dominated by forces and substances we do not yet understand. This new reality is encapsulated in our current standard model of cosmology, known as the lambda cold dark matter model, or lambda CDM. Lambda is the Greek letter Einstein once used for his cosmological constant, a fudge factor he later called his greatest blunder. It turns out he may have been right for the wrong reason, as his constant perfectly describes the steady push of dark energy. This model is the direct descendant of the Big Bang and inflation, incorporating a hot, dense beginning, a period of hyper-expansion, and a universe filled with dark matter and driven apart by dark energy. It is the framework that explains the cosmic microwave background, the large-scale structure of galaxies, and the accelerating expansion, all within a single, mathematically consistent story. Yet for all its success, lambda CDM presents us with the most profound puzzle of all. What, in the name of all that is physical, is dark energy? Dark energy is the dominant force shaping our cosmic future, but it is not the only ghost in the machine. Long before we knew the universe was accelerating, astronomers were wrestling with another invisible presence, one that holds the cosmos together rather than tearing it apart. This is dark matter, the universe's hidden skeleton. It is a substance that does not emit, absorb, or reflect any light, yet its gravitational pull is the fundamental architect of the universe's large-scale structure. Without it, galaxies would fly apart, and the majestic cosmic web we see today would never have formed. The story of its discovery begins not in the depths of space, but in the careful tracking of stars within a nearby spiral galaxy. In the 1930s, a brilliant and meticulous astronomer named Vera Rubin was studying the rotation of galaxies. She focused on the Andromeda Galaxy, our nearest large spiral neighbor. By measuring the speeds of stars and gas clouds at different distances from the galactic center, she could map out how the galaxy spins. According to Newton's and Einstein's laws of gravity, stars on the outskirts of a galaxy, far from the central bulge of visible mass, should orbit much more slowly than those near the center. Think of our solar system, where distant Pluto crawls along its orbit compared to Mercury, which whips around the Sun at blistering speed. This is what astronomers expected to see in galaxies. What Vera Rubin and her colleagues found was utterly different. Stars and gas clouds far out in the galactic suburbs were orbiting just as fast as those closer to the bright core. The entire galaxy was rotating like a rigid disk, a solid plate. This was impossible if the only gravity came from the stars, gas, and dust we could see. The only logical explanation was that galaxies are embedded within vast, spherical halos of invisible matter. This matter provides the extra gravitational glue to keep those high-speed outer stars from being flung off into intergalactic space. These flat rotation curves became the first robust observational evidence for dark matter. It was not a small amount either. The data implied that for every ounce of glowing, starry material in a spiral galaxy, there must be about 5 or 6 ounces of this dark, unseen mass holding it together. But how could we be sure this wasn't just a flaw in our understanding of gravity itself? Another line of evidence, even more dramatic, would come from watching how dark matter bends the fabric of reality. Gravity's hidden hand does more than spin galaxies. It weaves the largest pattern in existence. the quantum seeds we see in the cosmic microwave background were just the starting point. Over billions of years, under the relentless pull of gravity, those tiny overdensities grew, attracting more and more matter. They did not evolve in isolation, but as part of a vast, interconnected tapestry. This is the cosmic web, the grand architecture of the observable universe. On the very largest scales, matter is not scattered randomly. It is arranged in an intricate network of dense filaments, sprawling walls of galaxies, and immense, nearly empty voids that can span hundreds of millions of light years. Picture it as a three-dimensional spiderweb where the silken threads are chains of galaxy clusters, and the giant gaps between the threads are cosmic deserts of astounding emptiness. This is the universe's large-scale structure, and it is the direct, grown-up consequence of those infant quantum fluctuations. To see this structure, to map it, required a new kind of astronomy. Enter projects like the Sloan Digital Sky Survey. Beginning in 2000, this ambitious endeavor used a dedicated telescope to systematically image and measure the spectra of millions of galaxies across a huge swath of the sky. It was not just taking pictures, it was collecting precise three-dimensional addresses for galaxies, plotting their positions in space by measuring their redshifts. The resulting maps are nothing short of breathtaking. They reveal the universe in a way our eyes could never see, showing the ghostly filaments and bubbles in stunning detail. One of the most profound results from these galaxy surveys is a statistical measurement called the power spectrum. Scientists analyze the map and ask a simple but powerful question: how are the galaxies clustered? Do they tend to be separated by specific distances more often than others? The data reveals a clear, rhythmic pattern in the clustering, a preferred scale where galaxies are most likely to be found. This pattern is not random, it has a specific origin. In the hot, dense plasma of the early universe, sound waves propagated through the fluid. These were not sound waves as we know them, but vast pressure waves racing outward from every primordial overdensity at a significant fraction of the speed of light. When the universe became transparent at the release of the cosmic microwave background, those waves froze in place, imprinting a preferred scale on the distribution of matter. We see the fossil of that sound wave in the CMB as a specific size for the hot and cold spots, and we see its echo billions of years later in the galaxy surveys as a statistical preference for galaxies to be separated by a distance of about 500 million light-years. This is a direct link, a cosmic fingerprint that connects the infant universe to the adult cosmos. The statistical properties of the cosmic web, the sizes of the voids and the thickness of the filaments, match the predictions derived from the inflationary seeds seen in the Planck data with remarkable fidelity. It is a perfect bridge across time. The pattern we see in the sky today is not just consistent with inflation and the Big Bang, it is precisely what those theories demanded we find. The quantum whispers became gravitational seeds which grew into the majestic cosmic web we now chart. A web whose very threads confirm the story of our explosive birth. But to understand how those first structures truly grew, we need a telescope that looks not at galaxies, but at the space between them. That telescope is a quasar, the brilliant beacon of a supermassive black hole feasting on matter. Its light travels for billions of years to reach us, and on that epic journey, it passes through the tenuous gas that fills the cosmos. When astronomers analyze this ancient light with powerful spectrographs, they see something extraordinary. The quasar's smooth rainbow of colors is slashed by thousands upon thousands of narrow, dark lines. This is the Lyman Alpha Forest, one of the most beautiful and informative sights in all of astronomy. Each one of those dark absorption lines is a fingerprint. They are caused by clouds of neutral hydrogen gas, the most abundant element in the universe that float in the vast intergalactic voids. As the quasar's light passes through a cloud, the hydrogen atoms absorb a very specific shade of ultraviolet light, known as the Lyman alpha line. Because the universe is expanding, each cloud is moving away from us at a slightly different speed. This stretches the absorbed light, shifting it from the ultraviolet into the visible part of the spectrum we can observe from Earth. The result is a barcode of the cosmos. Each line tells us the exact redshift, and therefore the distance of a single hydrogen cloud along that one razor-thin line of sight. The closer the cloud is to us, the more its light is redshifted. So by reading this barcode from the blue end to the red, astronomers are effectively taking a core sample of the universe, drilling back through time from the present day to when the quasar's light first shone. The forest is not just a catalogue, it is a fossil record of the cosmic web in its infancy. Those hydrogen clouds are not random. They trace the underlying distribution of dark matter, the invisible skeleton of the universe. Where dark matter clumps together, its gravity attracts hydrogen gas. The densest knots become galaxies, but the vast filamentary strands of the web are traced by these diffuse, absorbing clouds. By mapping the intricate pattern of lines in the Lyman alpha forest from many different quasars, scientists can reconstruct a three-dimensional map of the early universe's matter distribution, a map made of light and shadow. This provides an independent, powerful test of our cosmic story. Does the clustering of these ancient hydrogen clouds match what inflation and our models of dark matter predict? Does it show the same statistical preferences, the same fingerprint of those primordial sound waves that we see in the galaxy surveys and the cosmic microwave background? The answer is a resounding yes. The Lyman alpha forest confirms that the seeds of structure we see in the CMB did indeed grow under the influence of gravity and dark matter into the vast cosmic web we observe at later times. It is a direct link between the smooth quantum beginnings and the clumpy universe of galaxies, written in the absorption lines of the most common atom in existence. These frozen sound waves left a permanent ruler etched into the cosmos. We call them baryon acoustic oscillations, a precise term for a beautifully simple idea. To understand them, we must return to that hot, dense plasma before the cosmic microwave background was released. In that searing fluid, ordinary matter, which scientists call baryons, was tightly coupled with light. Photons pushed outward with immense radiation pressure, while gravity, driven by both dark matter and the baryons themselves, pulled inward. This created a tug of war, a continuous series of pressure waves that rippled outward from every single one of those primordial overdensities. Picture dropping a pebble into a still pond. A circular wave expands outward from the point of impact. Now imagine dropping billions of pebbles simultaneously into a pond of cosmic proportions, each creating its own expanding ring. That was the early universe, alive with overlapping sound waves racing through the plasma at over half the speed of light. This cosmic symphony had a timer. When the universe cooled enough for atoms to form at recombination, the music stopped abruptly. The photons decoupled and streamed away as the cosmic microwave background, and the baryons, suddenly free from the photon pressure, were left frozen in place. The result, every initial overdensity became surrounded by a spherical shell of matter, a frozen ripple exactly one sound traveled distance wide. This distance became a standard ruler, a preferred scale imprinted on the cosmos. That shell is the acoustic peak. On the largest scales, this means matter is more likely to be found separated by this specific distance than any other. It appears in the cosmic microwave background as the characteristic size of the hot and cold spots, but its true power is revealed billions of years later in the galaxy surveys like the Sloan Digital Sky Survey. When astronomers map the three-dimensional positions of millions of galaxies, they perform a statistical analysis on their clustering. They are not looking for individual shells, but for a subtle statistical preference, a faint echo in the data that says galaxies are more likely to be separated by about 500 million light-years than any other distance. That number is the grown-up version of that frozen sound wave, stretched by the expansion of the universe. This baryon acoustic oscillation scale is a gift to cosmologists. Because we know its original size from our understanding of the early universe's physics, it acts as a perfect calibration tool. By measuring how much this standard ruler appears stretched in the ancient universe versus the more recent universe, we can chart the expansion history of the cosmos with extraordinary precision. It provides an independent measurement of dark energy's influence, confirming the acceleration story told by the supernova. Finding this same scale in both the infant universe's CMB and the adult universe's galaxy distribution is a breathtaking confirmation of our entire cosmic narrative, linking the first moments directly to the structure we see today. The cosmic symphony left a perfect ruler, but it also erased a ghost. Among the most compelling arguments for cosmic inflation is a problem that vanished before we even knew it existed: the mystery of the missing magnetic monopoles. In our everyday experience, magnets always come with two inseparable poles, a north and a south. Break a bar magnet in half, and you do not get isolated poles. You get two smaller magnets, each with its own north and south. This is a fundamental feature of the electromagnetism we know. Yet, many of our most ambitious theories of physics, the grand unified theories that attempt to merge the fundamental forces, make a startling prediction. In the extreme energies of the universe's first split second before the forces of nature differentiated, exotic particles should have formed. Among them would be magnetic monopoles, particles that carry only a north or only a south magnetic charge. These would not be mere curiosities. They would be incredibly massive, perhaps as heavy as a bacterium yet smaller than a proton, and staggeringly dense. According to these theories, the seething energy of the early cosmos should have produced them in prodigious numbers, a relic population that should still be drifting through space today. The problem is, we have never found one. Not a single definitive magnetic monopole has ever been observed, despite decades of sensitive searches in particle accelerators, cosmic rays, and even in the material of moon rocks. Their complete absence was a glaring contradiction, a threat to otherwise elegant theories. If the grand unified theories were correct, the universe should be flooded with these monstrous particles, yet our reality is conspicuously clean. This was the monopole problem. Inflation provided an elegant and devastatingly simple solution. Remember that exponential stretching, that moment when a subatomic patch of space ballooned to cosmic size. If magnetic monopoles were produced in that first instant before inflation began, they would have been incredibly numerous but packed into an unimaginably tiny volume. Then inflation switched on. Space itself expanded by a factor of at least 10 to the 78, a number so vast it defies analogy. This hyper-expansion did not create new monopoles, it simply took the ones that already existed and flung them impossibly far apart. It diluted their density to virtually zero across the entire observable universe. Imagine a few grains of sand scattered on a deflated balloon. Now inflate that balloon to the size of the observable universe. The chance of ever finding one of those original grains of sand in your corner of the balloon becomes infinitesimally small. That is what inflation did to magnetic monopoles. Their predicted absence is not a failure of the grand unified theories, but a triumphant postdiction of inflation. The theory elegantly explains why we do not see them, not because they were never made, but because they were scattered into the cosmic deep by the most violent expansion imaginable. This solution is so compelling that many physicists consider it one of inflation's three great successes, alongside solving the horizon and flatness problems. It turned a potential crisis into a quiet confirmation, proving that sometimes the most powerful evidence is the profound silence where we expected a roar. The profound silence of missing monopoles points to a universe stretched beyond recognition, a stretching that left another indelible mark on its shape. Multiple, independent lines of investigation have now converged to measure the geometry of the cosmos itself, and the answer is precise and unanimous. The universe is flat, not flat like a sheet of paper, but flat in the cosmic sense, meaning its large-scale geometry obeys the rules of classic Euclidean geometry we learned in school. The angles of a giant triangle drawn across billions of light years would add up to exactly 180 degrees, and parallel laser beams would never meet or diverge. This is not a guess, it is a measurement, and the precision is staggering. Data from the cosmic microwave background, particularly from the Planck satellite, provides the tightest constraint. By analyzing the specific pattern of hot and cold spots in the afterglow, scientists can deduce how much the fabric of space is curved. Planck's final maps revealed a universe that is flat to within a margin of error of just 0.2%. This is like surveying the entire Earth and finding its surface deviates from perfect flatness by less than the height of a small hill. But the CMB is not the only witness. The Baryon acoustic oscillations, those frozen sound waves imprinted in the clustering of galaxies, act as a standard ruler. If the universe were positively curved like a sphere, that ruler would appear larger to us. If it were negatively curved like a saddle, it would appear smaller. Measurements from galaxy surveys like Sloan find the ruler is exactly the expected size, confirming flatness from a completely different epoch and method. Even the distant supernova that revealed dark energy add their voice to the chorus. The apparent brightness and redshift of these exploding stars across cosmic time are consistent only with a flat universe containing dark energy. These three powerful probes, each observing different phenomena at different times, all point to the same geometric truth. This flatness is far more than a curious fact. It is a direct and stunning prediction of cosmic inflation. Think of a tiny, wrinkled raisin. If you could inflate that raisin to the size of the Earth, its surface, from the perspective of an ant crawling on it, would appear perfectly smooth and flat. Any initial curvature or wrinkle would be stretched out of existence. Inflation did exactly this to the infant universe. No matter what bizarre, knotted shape it may have been born with, that hyper-expansion of space by a factor of trillions upon trillions would have ironed it into geometric flatness. The measured flatness we see today is not a miraculous starting condition. It is the inevitable consequence of that explosive growth spurt. It is the stretched canvas upon which the entire subsequent history of the cosmos has been painted. This convergence of evidence is one of the strongest pillars supporting our modern cosmic story, telling us that the universe's shape is a direct relic of its first, most violent moment. Flat geometry is a triumph, but it has revealed a crack in our cosmic foundation. A precise and growing discrepancy now threatens the harmony of our standard model, a puzzle astronomers call the Hubble tension. At its heart is a simple question with two conflicting answers. How fast is the universe expanding right now? We measure this current expansion rate with a number called the Hubble constant. For decades, scientists have pursued two independent paths to pin down this fundamental speed limit of cosmic growth. The first path looks back to the infant universe, using the exquisitely detailed map from the Planck satellite of the cosmic microwave background. By analyzing the subtle patterns in that ancient light, the physics of the early cosmos, and assuming our standard lambda CDM model is correct, we can extrapolate forward 13.8 billion years to calculate what the expansion rate should be today. This is a top-down, model-dependent approach. The second path measures the rate directly in our local, modern universe. Astronomers use cosmic ladders, starting with pulsating stars called Cepheid variables in nearby galaxies to calibrate the true brightness of more distant Type 1, a supernova. By observing how dim these brilliant standard candles appear, they can measure distances across millions of light years, and by pairing those distances with redshift measurements, they directly calculate the Hubble constant. This is a bottom-up direct measurement. Both methods are incredibly sophisticated, backed by teams of brilliant scientists and decades of painstaking work. And they disagree. The Planck measurement from the early universe suggests a Hubble constant of about 67 kilometers per second per megaparsec. The supernova and Cepheid measurements from the late universe consistently find a faster rate, around 73. The difference is only a few percent, but the uncertainty margins for each method have shrunk so dramatically that they no longer overlap. This is not an error, it is a tension, a stubborn and statistically significant gap that has persisted and even grown as measurements have become more precise. Why does this matter so profoundly? Because in a universe governed by a single set of physical laws, there should be only one true expansion rate. If two impeccably careful methods, looking at opposite ends of time, yield different answers, it suggests something in our model is incomplete or incorrect. Perhaps dark energy is not a constant but an evolving force that has changed strength over cosmic history. Maybe there is an unknown type of neutrino or other relativistic particle that zipped through the early cosmos, subtly altering the sound waves we see in the CMB. Or, most intriguingly, it could point to a flaw in our understanding of gravity itself, or even hint that cosmic inflation deposited some unexpected feature that has subtly warped the universe's expansion timeline. The Hubble tension is more than a technical discrepancy, it is a potential doorway. It tells us that our otherwise magnificent model of the cosmos, which so perfectly explains the CMB, the cosmic web, and the abundance of light elements, might be missing a piece. Solving this puzzle could be the first step toward the next great revolution in cosmology, revealing a deeper layer of reality hidden within the simple question of how fast space is stretching. That precise cosmic fingerprint from the first 3 minutes holds a single, stubborn smudge. The predictions for helium and deuterium match the pristine clouds of the early universe with stunning accuracy, a triumph of Big Bang nucleosynthesis. But for the third lightest element, lithium, the story breaks down. The calculations tell us that a specific isotope, lithium-7, should be about 3 times more abundant in these ancient stellar atmospheres than what astronomers actually measure. This is the lithium problem, a quiet but persistent anomaly that has endured for decades. It is not a catastrophic failure of the Big Bang theory, but a fascinating puzzle, a loose thread in an otherwise tightly woven tapestry. The oldest stars in our galaxy, known as population 2 stars, act as cosmic time capsules. They formed from nearly pure material left over from the Big Bang, and their atmospheres preserve that original chemical mix. When we analyze their light, the helium and deuterium lines sing in perfect harmony with the predictions. The lithium line, however, comes out as a faint whisper where we expect a clear note. So where did the lithium go, or was it never made in the amounts we think? One set of possibilities points to the stars themselves. Perhaps these ancient, slow-burning stars have internal processes we do not fully understand that slowly destroy lithium over billions of years, dredging it down from their surfaces into hot interiors where it fuses into other elements. Or maybe the models of stellar atmospheres themselves are subtly off, causing us to misinterpret the strength of the lithium absorption lines we see. Another avenue looks back to the nuclear physics of the first 3 minutes. The reaction rates that transformed protons and neutrons into lithium nuclei are incredibly complex, involving chains of rare interactions. A slight revision to one of these poorly measured nuclear cross-sections could, in theory, lower the predicted yield. The most exotic solutions venture into new physics. Could an unknown particle, like a certain type of decaying dark matter, have been present in those first minutes, altering the nuclear balance? Or is it possible that the universe was not perfectly uniform during nucleosynthesis, with pockets of slightly different density changing the outcome in certain regions? The lithium problem endures precisely because it is small enough to be a detail, yet precise enough to be a clue. It reminds us that even our most successful cosmic models have unresolved corners. Solving it might not overthrow our story of the Big Bang, but it could reveal a subtle, missed chapter in the narrative of creation, written in the faint spectral lines of the universe's oldest stars. Lithium's faint whisper is a puzzle for the future, but one question overshadows all others. We have traced the story of cosmic inflation from its quantum seeds to the flat universe it created, yet the central character remains a ghost. What was the inflaton field? This is not just a detail, it is the engine of creation itself, the mysterious energy that powered the universe's explosive growth spurt. Identifying this field is the next great frontier in cosmology, a quest that could finally bridge the largest and smallest scales of reality. In our current understanding of physics, fields are everywhere. They are fundamental entities that fill all of space, and particles are merely excitations or ripples in these fields. The electromagnetic field gives us light. The electron field gives us electrons. The Higgs field gives mass to fundamental particles. Inflation proposes that in that first split second, another field dominated the cosmos, a scalar field similar to the Higgs. A scalar field has a value at every point in space, like a temperature or a pressure, but no direction. Think of it as a vast, invisible landscape of energy. The inflaton field is imagined as resting in a high-energy state, like a ball perched at the very top of a perfectly flat plateau. This unstable configuration possessed a peculiar property. Its energy density did not quickly dilute as space expanded. Instead, it acted like a form of anti-gravity, causing space to stretch at an exponential rate. As the field slowly rolled down its gentle slope, inflation eventually ended, and its pent-up energy decayed in a fiery cascade, reheating the universe into the hot soup of particles of the classic Big Bang. So what could this field actually be? The most tantalizing candidate is one we already know, the Higgs field. Perhaps in the extreme energies of the early universe, the Higgs played a dual role, both giving particles mass and driving cosmic inflation. Other theories propose entirely new scalar fields, predicted by extensions to the standard model of particle physics, like those suggested by supersymmetry. These fields would have no role in today's cold, quiet universe, lying dormant and invisible except for the colossal structural legacy they left behind. The search for the inflaton is a two-pronged mission. The first path looks to the sky, to the cosmic microwave background. The specific pattern of the primordial density fluctuations, especially that slight tilt measured by Planck, is a direct readout of the inflaton field's landscape. The detailed shape of its potential energy hill, whether it was steep or shallow, curved or straight, is encoded in the statistics of those hot and cold spots. Future missions that map the CMB's polarization with even greater precision, hunting for the elusive B-mode signal of primordial gravitational waves, could measure the energy scale of inflation itself. That number would tell us if the inflaton operated at energies 1 trillion times beyond the reach of any particle collider, or if by some slim chance it might be within our grasp. This leads to the second, breathtaking possibility. If the energy scale of inflation was low enough, the inflaton particle itself, the ripple in that field, could potentially be produced in a next-generation particle collider. We might not need to look billions of light-years away, but could recreate a whisper of the universe's first moment in a laboratory on Earth. Discovering the inflaton would be the ultimate unification. It would tie the physics of the infinitesimal quantum world directly to the fate of the entire cosmos, revealing that the laws governing the smallest particles are literally responsible for the existence of space, time, and everything within it. The quest is to find the architect of reality. The inflaton field may have been the engine for our universe, but what if it never truly shut off? This leads us to one of the most mind-bending ideas in modern cosmology, a speculative consequence of inflation known as eternal inflation and the multiverse. Picture the inflaton field's landscape not as a single hill, but as a vast rolling terrain. In most regions, the field would roll down into a valley, ending inflation and creating a hot Big Bang universe like our own. But according to some models, the quantum fluctuations within the inflattened field itself could be powerful enough to create a runaway effect. In certain pockets, random quantum jumps could keep pushing the field back up the energy hill, even as the surrounding space settles down. In these regions, inflation would continue forever. Space in these eternally inflating zones would expand so much faster than in the stable pockets that they would dominate the overall volume of reality. Our entire cosmos, with all its hundreds of billions of galaxies, would be just one tiny bubble, one stable pocket, in an infinite, ever-growing sea of inflating space. And here is where the idea truly expands. Each time inflation ends in a local pocket, it does so with a slightly different roll of the quantum dice. The physics of that decay, the way the inflattened field's energy converts into particles, could set the fundamental constants of nature for that newborn universe. The strength of gravity, the mass of an electron, the number of spatial dimensions that stabilize, these could all be different in other bubbles. This is the inflationary multiverse, a cosmic froth of potentially infinite pocket universes, each with its own unique laws of physics. In some, gravity might be so strong that stars form and burn out in an instant. In others, the nuclear forces might be too weak for atoms to ever bind, leaving a sterile sea of hydrogen. Our universe, with its precise constants that allow for atoms, stars, planets, and life, would be just one rare, habitable bubble in a vast and mostly inhospitable ensemble. This idea is not a proven fact. It is a staggering implication drawn from the mathematics of certain inflationary models. It pushes cosmology into profound philosophical territory. If true, it offers a dramatic answer to the question of why our universe seems so finely tuned for life. There is no fine-tuning because every possible set of constants exists somewhere in the multiverse. We simply find ourselves in one of the rare bubbles where conditions allowed observers like us to arise. This is known as the anthropic principle, yet this very power is also the source of intense debate. If other universes are causally disconnected from ours, forever beyond the reach of any signal, even light, can we ever call this a scientific theory? Science thrives on testable predictions and falsifiable evidence. How do we test for something that exists outside our cosmic horizon? Proponents argue that the multiverse is a natural prediction of our best theories of inflation and quantum mechanics, and that we can look for indirect evidence like specific patterns in our own cosmic microwave background that might suggest a collision with another bubble universe in the distant past. Critics contend that without a direct test, it risks becoming a metaphysical idea, an untouchable explanation that can account for anything. The debate cuts to the core of what cosmology can and should explain. Does our quest for origins inevitably lead us to realities we can never observe? The multiverse remains a frontier of thought, a breathtaking possibility that stretches the meaning of reality itself, born from the same equations that gave us our own spectacular beginning. Our cosmic story is not yet a closed book. While inflation stands as the dominant and spectacularly successful framework, the quest for truth demands we listen to other voices. Competing theories offer radically different prologues to the Big Bang, challenging the very notion of a singular beginning. Among these alternatives is the elegant, almost poetic cyclic model. Imagine not a single explosive birth, but an endless cosmic heartbeat. In this vision, our expanding universe is not the first and only act. Instead, it is one phase in an eternal cycle of expansion, contraction, and rebirth. The model suggests that the dark energy currently accelerating our expansion will eventually transform, leading to a gradual slowdown, a halt, and then a gentle contraction over trillions of years. All matter and energy would draw together, not into a singular point of infinite density, but into a dense, hot state that then bounces, triggering a new period of expansion, a new Big Bang. This bounce replaces the need for a singular beginning from nothing. The cyclic model aims to solve the same horizon and flatness puzzles as inflation, but through a different mechanism. In this view, each cycle stretches and flattens the universe over an immense duration, smoothing out irregularities and setting the stage for the next. It even offers a potential origin for the quantum seeds of structure generated during the chaotic dynamics of the bounce itself. Its key prediction is a specific, subtle pattern in the cosmic microwave background that differs from inflations, particularly in the polarization signals, a signature future telescopes might one day detect. Another challenger emerges from the realm of string theory. String gas cosmology proposes that before the Big Bang, the universe was a hot, dense, and static gas of the fundamental strings postulated by string theory. In this compact, winding state, space could not expand. Then, a phase transition occurred like ice melting into water. The strings unwound, and 3 dimensions of space were allowed to rapidly expand, giving us our familiar universe while the remaining dimensions remained tightly curled up. This model naturally produces a nearly scale invariant spectrum of fluctuations, not from quantum jitters during hyper-expansion, but from thermal fluctuations in that primordial string gas. It also predicts distinct signatures, such as a slight break from perfect scale invariance on the very largest scales, and a specific type of non-Gaussian pattern in the CMB statistical fingerprints that are different from those of simple inflation. The existence of these alternatives is not a weakness of cosmology, but its greatest strength. It signifies a field alive with debate, driven not by dogma, but by a relentless desire to test every possible path to truth. Each theory, inflation included, makes specific, differing predictions about what we should see in the faint light of the cosmic microwave background and the clustering of galaxies. The next generation of observatories with even sharper eyes on the primordial sky will be our arbiters. They will measure the polarization patterns, the statistical nuances, and the faintest whispers of gravitational waves with precision we can now only dream of. The data will guide us, potentially confirming one paradigm, forcing a dramatic synthesis, or sending us back to the drawing board for an idea we have not yet conceived. This dynamic tension is the engine of discovery, reminding us that our understanding of the cosmos is a story still being written, with its most revolutionary chapters perhaps still ahead. The ultimate test of our cosmic story will come from the next generation of eyes on the sky. While our current telescopes have painted a magnificent picture, the finer details and deepest mysteries demand instruments of even greater power and precision. A new era of observatories is now being built, designed to probe the shadows of dark matter, measure the push of dark energy, and finally capture the whisper of inflation's gravitational waves. These are not incremental upgrades, they are machines built to answer existential questions. First, from a mountaintop in Chile, the Vera Sea, Rubin Observatory will soon begin the legacy survey of space and time. Its primary mirror is wider than a tennis court, and its camera is the largest digital eye ever built for astronomy. For a decade, it will scan the entire southern sky every few nights, creating an unprecedented motion picture of the cosmos. It will catalog billions of galaxies, mapping the cosmic web in 3 dimensions with staggering detail, but its true power lies in seeing the unseen. By observing how the light from distant galaxies is subtly warped by the gravitational pull of invisible mass, a phenomenon called weak gravitational lensing, Rubin will create the most precise maps of dark matter ever made. It will watch for the subtle stretching of the Barrian acoustic oscillation ruler across cosmic time, providing an independent, ultra-precise measurement of dark energy's influence on the expansion of the universe. This relentless survey will also find millions of supernovae, building a richer, deeper history of cosmic acceleration. Following Rubin into space will be the Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer. Roman is often called Hubble's wide-eyed cousin. It will possess Hubble's sharp vision but over a field of view 100 times larger. This allows it to conduct vast, deep surveys at infrared wavelengths, peering through cosmic dust to see the earliest stages of galaxy formation. Roman will take weak lensing and baryon acoustic oscillation measurements to a new level of accuracy, free from the blurring effects of Earth's atmosphere. Its deep surveys will help determine whether dark energy has remained constant over time, as Einstein's cosmological constant suggests, or if it has evolved, which would point toward a more dynamic and exotic force. Perhaps most critically, Roman will work in tandem with Rubin, cross-calibrating observations to eliminate systematic errors and deliver a definitive, joint measurement of the universe's expansion history, directly confronting the Hubble tension. Yet, to peer into the very first instant, we must return to the oldest light. A new generation of cosmic microwave background experiments is preparing to hunt for the Holy Grail, the primordial B-mode polarization. Projects like CMB Stage 4 or CMBS-4 represent a colossal leap. This ambitious ground-based experiment will deploy 500,000 ultra-sensitive detectors across telescopes in Chile and at the South Pole. Its goal is to measure the polarization of the CMB with a sensitivity 50 times greater than any previous effort. CMB-S4 will stare down the foreground contamination from galactic dust with such precision that it can subtract it with near-perfect fidelity. If the signal of inflationary gravitational waves is there at a level within theoretical reach, this experiment is designed to find it. A detection would not only confirm inflation beyond any reasonable doubt, but the strength of the signal would tell us the energy scale at which inflation occurred, directly linking this cosmic event to specific theories of particle physics. A non-detection, however, would be equally profound, ruling out a wide swath of the simplest and most popular inflationary models and forcing theorists back to the drawing board. These observatories, along with future space-based CMB missions now in planning, represent a coordinated assault on the universe's greatest secrets. They will move us from an era of mapping what is there to an era of understanding why it is that way. The data they collect will either cement our current cosmic paradigm or reveal the cracks that lead to the next revolution. We are building the machines that will write the next chapter of our origin story. From a single, searing point of infinite potential, our cosmos has unfolded into a breathtaking tapestry of galaxies, stars, and planets. This incredible journey, traced through 25 profound discoveries, is the story of how everything came to be. We have followed the evidence from Hubble's fleeing galaxies to the faint hiss of the cosmic microwave background, from the perfect recipe of light elements forged in the first 3 minutes to the quantum whispers stretched across the sky. Cosmic inflation provided the crucial prologue, a moment of hyper-expansion that set the stage for a flat, smooth, and structured universe. Dark matter sculpted the cosmic web, and dark energy now scripts its accelerating future. Each puzzle solved, from the horizon problem to the missing monopoles, has woven a coherent and majestic narrative of our origins. Yet for all we have learned, the mystery only deepens. We still do not know the true nature of the inflaton field, the substance of dark matter, or the force of dark energy. The Hubble tension and the lithium problem whisper that our map is not yet complete. This is not an ending, but an invitation. The next time you look up at the night sky, see it for what it truly is, a living relic of creation. Those points of light are the grandchildren of quantum fluctuations, born in a fireball and shaped by invisible hands across 14 billion years. It is a story that belongs to all of us. What part of this cosmic journey fills you with the most wonder? Share your thoughts below, and join us as we continue to explore the greatest mysteries of space and time.